In today's video, we will be looking at limits that result in what's known as an indeterminate form. Now, what is an indeterminate form? Well, if we're given a function f, if the formula for f of c yields an undefined expression in one of the forms, zero over zero, infinity over infinity, infinity times zero, or infinity minus infinity, then we say that f of x has an indeterminate form or is indeterminate at x equals c. Now, if a limit produces an indeterminate form, there are a couple of ways we can go about evaluating it. The first way is by using algebra and this proposition, which states if f of x equals g of x, when x is not equal to a, so when f of x and g of x are identical everywhere except at x equals a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided the limit exists. So the idea here would be to use algebra to simplify f of x into a new function g of x, which is identical to f of x everywhere except at x equals a. Then we can evaluate the limit of this new function, and that would be the same as the limit of the original function. The other way of evaluating it would be by using a theorem known as the squeeze theorem. Now, let's consider the limit as x approaches a of some function g of x. If for every x in the domain of g, except possibly at a, there are functions f of x and h of x such that f of x is less than or equal to g of x, less than or equal to h of x. Then it would appear that all three functions are approaching the same value. as x approaches a. So the idea here is if we look at the graph, so let's go ahead and sketch a graph. Let's say this is our value a here. Let's make this function our g of x here. Okay, now let's say this would be our f of x. And then we can do something like, oh, that's not going to work. Say that there would be h of x. I'm going to draw this too. I'm going to move my a to be right here. Notice then that essentially what's happening is the values of g of x are getting squeezed to one value, specifically f of a and h of a. This is the essence of the squeeze theorem, which I'm now formally going to state. So we let f of x, g of x, and h of x be defined for all x that's not equal to a over an interval that contains a. If f of x is less than or equal to g of x, which is less than or equal to h of x, for all x that is not equal to a in an open interval that contains a, and we have the limit as x approaches a of f of x equal to the limit as x approaches a of h of x, and we'll say that equals some value L, where L is obviously a real number, then we can conclude that the limit as x approaches a of g of x must also be L. What we now wish to do is evaluate two special trigonometric limits. The first is we want to look at the limit as theta approaches 0 of sine of theta over theta. The first thing that we're going to do is we're going to look at the limit of sine of theta. Right, so to do this, let's look at a unit circle. Let's say this is our unit circle. We have this ray here, makes an angle of theta. And obviously this is the point here, 1, 0. This point up here is the point cosine theta, sine theta. Now what we do is we draw a vertical line from the point that has a length of sine of theta. And we also note that this arc has an arc length of theta. So what this means is for 0 less than theta less than pi over 2, which is the entire first quadrant, we would have 0 is less than sine of theta, which is less than theta. Now, what we can do is let's look at the limit as theta approaches 0 from the right. Well, 0, that is just 0. If we also look at the limit as theta approaches 0 from the right of just theta, that is also 0. Therefore, by the squeeze theorem, the limit as theta approaches 0 from the right of sine of theta must also be 0. So we now have the right-handed limit of sine of theta. To get the left-handed limit, what I'm going to do is notice for negative pi over 2 less than theta less than 0, we can write this as 0 less than negative theta less than pi over 2. What we do is we just multiply this entire inequality by -1. And remember, when you multiply by a negative, the inequalities flip. Right? So if we were to multiply by a negative, this would become greater than, this would become greater than. So, using the argument from above, we would have that 0 is less than sine of negative theta, which is less than pi over 2. However, since sine is an odd function, we can write this as 0 less than negative sine of theta less than pi over 2. I'm sorry, this is not pi over 2. This should be theta. Should be negative theta. Now we can multiply again through by -1, and we'd have theta is less than sine of theta, which is less than 0. Now, again, this is for the case where we're in quadrant 4. Now, we can approach theta from the left, right? We can approach 0 from the left, right? Because theta is less than 0 now. So, what we notice, limit as theta approaches 0 from the left of theta is 0, and the limit as theta approaches 0 from the left of 0 is also 0. Once again, using squeeze theorem, we can conclude that the limit as theta approaches 0 from the left of sine of theta is also 0. Since the right-handed limit is equal to 0, and that also happens to be the left-handed limit, then we can conclude that the limit as theta approaches 0 of sine of theta is equal to 0. We can now use this along with a new unit circle to evaluate our desired limit. So let's look at a new unit circle. Once again, this is the point 1, 0. We're going to have our ray that makes an angle theta. Now we once again have a straight vertical line. That is sine of theta, length sine of theta. Once again, this arc will have a length of theta. Except now, let's draw a new vertical line. Sorry. That goes from this point straight up to the ray. Now this is going to have a length of tangent of theta. Now what we've done here is made two triangles. So we can see that for 0 less than theta less than pi over 2, again, we're only in the first quadrant. Sine of theta is less than theta, but now theta is less than tangent of theta. This will allow us to write that 1 is less than theta over sine of theta, which is less than tangent of theta over sine of theta, which reduces to 1 over cosine of theta. What we now do is take the reciprocal of everything in the inequality, and once again, when you take a reciprocal, you're flipping the inequality, so we can write cosine of theta is less than sine theta over theta, which is less than 1. Our goal here is to use the squeeze theorem as theta approaches 0, which means we need to now evaluate the limit of this function here. So limit as theta approaches 0 of cosine of theta. Well, cosine of theta we can write as the limit as theta approaches 0 square root of 1 minus sine squared theta. Right here, what we're doing is we're using Pythagorean identity cosine squared theta plus sine squared theta is equal to 1. This allows us to say that cosine of theta would be plus or minus the square root of 1 minus sine squared of theta. However, we're working right here in the first quadrant, and we know that cosine has to be positive in that quadrant. That is why we can ignore the negative part, and we just take cosine to be positive. Well, this would give us the square root of the limit as theta approaches 0 of 1 minus sine squared, which now allows us to do this using limit laws. But we know that this limit right here is 0. So this is now essentially the square root of 1 minus 0 squared, and that is just 1. So the limit as theta approaches 0 of cosine of theta is equal to 1. Now what we can do is relook back at this inequality up here. The limit as theta approaches 0 from the right of cosine of theta is 1. The limit as theta approaches 0 from the right of 1 is also 1. So the limit as theta approaches 0 from the right of sine of theta over theta is 1. Now if we do a similar manipulation as we did here, so negative pi over 2 to less than theta less than 0, it can be shown that the limit as theta approaches 0 from the left of 1 is equal to 1, and that is going to be the limit as theta approaches 0 from the left of cosine of theta, which means that the limit as theta approaches 0 from the left, sine of theta over theta is equal to 1. The actual workout of this is going to be left to the viewers. This allows us to conclude that the limit as theta approaches 0, sine of theta over theta is 1. Now we wish to look at this limit. We're going to do a little bit of work first. Let's take a look. And let's do conjugation. So we're going to multiply numerator and denominator by 1 plus cosine of theta. Doing this, we now have the formula for difference of squares, so this will become 1 minus cosine squared theta all over theta times 1 plus cosine of theta. Using the Pythagorean identity introduced earlier, we can write 1 minus cosine squared as just sine squared, and so we're left now with this. And this is true as long as theta was not equal to 0. This allows us to now come up and use this proposition. Right? I just found an equivalent function g of x everywhere except at 0. So if we take the limit of this function right here, it'll be the same as the limit of this. Now we're going to have to be a little clever. We can write this fraction as a product of two fractions, specifically sine theta over theta times sine of theta over 1 plus cosine of theta. We can now use the appropriate limit law to write limit theta approaches 0, sine of theta over theta, then multiply that by the limit as theta approaches 0 of sine of theta over 1 plus cosine of theta. Now we've already evaluated this limit. This limit was 1. All that's left is to evaluate this limit here. Again, using appropriate limit laws, we can write it this way. Now this limit up here is 0. Then that limit is 1. And this limit we just showed was 1. So we get 0 over 2, which is 0. So the limit as theta approaches 0 of 1 minus cosine theta all over theta is equal to 0. Now, a quick observation, keep in mind that if we had this limit here, cosine theta minus 1 all over theta, well, this would be limit as theta approaches 0, negative 1 minus cosine theta all over theta. Using the appropriate limit law, we can factor out that negative 1. And we just saw that limit was 0. So the order in which you're doing the subtraction here doesn't actually matter. You'd still wind up with 0. We will now conclude this video by looking at several examples. So let's go ahead and look at this limit first. Now, if we go ahead and plug in 3, we'll wind up with 9 minus 9 over 18 minus 15 minus 3, which winds up giving us 0 over 0. This is indeterminate. So let's go ahead and do some algebra. Look at x squared minus 3x over 2x squared minus 5x minus 3. And our goal is to try and simplify this. So let's factor numerator and denominator. We can factor an x from the numerator. And now the denominator. Right, so x and 2x. 3 and 1. Then minus and plus. Those will cancel out. And we will now be left with x over 2x plus 1. And this, of course, is valid as long as x is not equal to 3. Well, we can now use the proposition to say that our limit must be equal to the limit of this new function. Now if we plug in 3, we'll get 3 over 7. Okay, so now let's look at this limit. Again, if we go ahead and plug in negative 1, we will have square root of 1 minus 1 all over negative 1 plus 1. That winds up leaving us with 0 over 0. This is indeterminate. So again, we're going to need to do some algebra to try and simplify this. Here what we can do is we can rationalize. So multiply numerator and denominator by the square root of x plus 2 plus 1. Now the numerator is different to squares, so we'll have x plus 2 minus 1, and then x plus 1 times that square root of x plus 2 plus 1 in the denominator. Numerator will simplify to just x plus 1. Right, we can now cancel out the x plus 1's. And this would only be valid when x is not equal to negative 1. Again, this allows us to use our proposition to say that our original limit is equal to the limit of this new function. Plug in negative 1, 1 over the square root of 1 plus 1, which is a half. All right. Let's now look at this limit. Again, let's plug in x equals 1. Let's see what we get. We'll have a half minus a half over 1 minus 1. This will give us, once again, 0 over 0, which is indeterminate. So let's try and simplify. So in the numerator, we have to add fractions, and remember to do that, we need a common denominator. In this case, our common denominator will be 2 times x plus 1. And so we're going to wind up with, in the numerator, 2 minus the quantity of x plus 1. Now that whole thing will be over x minus 1. If we simplify, we'll wind up with 1 minus x over 2 times x plus 1. And when you divide fractions, you multiply by the reciprocal. In the numerator, you can factor out a negative 1. Now we can cancel out x minus 1's, and we'll be left with negative 1 over 2 times x plus 1. And this is all valid as long as x is not equal to 1. This allows us, once again, to use our proposition. So our limit is now equal to the limit of this new function. We'll wind up with negative 1 over 2 times 2, and so we have negative 1/4. Right, let's now look at this limit. Okay. If we try to plug in 0, it's something that looks like 1 over 0 plus 5 over 0, which is effectively infinity minus infinity. This is indeterminate. Again, let's do some algebra. We look at 1 over x plus 5 over x times x minus 5. We need a common denominator. All right, so the common denominator is x times x minus 5. We'll have x minus 5 plus 5. That simplifies to x over x times x minus 5. We can cancel out the x's. We'll be left with 1 over x minus 5, valid as long as x is not 0. So our limit is now equal to the limit of this new function, and that limit winds up being negative 1/5. And so that concludes our video on indeterminate forms. The next video in this series is going to look at a formal definition of continuity.